Mic check. Sweet. All right, welcome to Extension 2. This is by far the best HSC course, and it's the best scaling course, and it's the most interesting course, and it brings together a lot of stuff from physics and engineering and stuff like that. So I genuinely believe it's the best course in offer. But I guess let's just get straight into it. So this is going to be kind of like an pre-introduction to complex numbers. We're going to sort of look at why complex numbers are a thing or how they might have been discovered. But it's just kind of like a bit of a discussion. It would have been cool to do this in class, but obviously we can't. If you look at the top left here, this is kind of our sequence for the beginning. So we've got this is the prologue. Then we'll start looking at what a complex number actually is, and then we'll kind of go from there. So I'm also playing around with this black background, and I've just noticed that the laser looks really cool. And I kind of just want this because it's got lines that you can see on the stream. I believe that you can't really see them if they're all white. So anyway, let's kind of look at what you already know, and I guess how we can build on that to kind of discover complex numbers for ourselves, because it's genuinely something that someone probably did one day and they were like, oh, this is a thing. Anyway, so pretty much leading up to this course, it's kind of been assumed that when you have a number or a letter, let's call it x, that when we square it, the result is always either 0 or positive. So you can say it's always 0 or positive, so greater than or equal to 0. And so there's no real number I can chuck in here such that it's going to be less than 0. I can't square something and become negative. Okay, and we call the solutions to these real. And you might have heard that before, but we just say that x in this case is real. Another way of saying that is x is a part of the real numbers, which is something we'll talk about soon. This is going to be a bit of a scribble, by the way. There's better notes on the classroom. Yeah, so we call those things real numbers, and then we start to look at, okay, well, that's kind of a simple quadratic equation, quadratic being because it's to the power of 2. So what if we looked at equations of the form ax squared plus bx plus c equals 0. So if I wanted to solve these things, rather than thinking about when they're greater than or equal to 0, what about how do I find values for x such that this expression equals 0? And so then, you would have seen various numbers put in here. So like 2x squared, what have I got? Minus 9x plus 7. So maybe I want to know when that equals 0. And we have a million techniques to solve something like this. We could factorize it. It's got a 2 here, so that means I'd have to factorize it differently. I might want to use a quadratic formula. I could complete the square, but at the end of the day, this thing does factorize nicely to 2x, was it minus 7x minus 1? And then I can solve that for x. I can say, leave a line, I can say x is equal to 7 on 2, or it's equal to 1. Okay, and so they were our solutions to this quadratic equation. They have a few different names. You might call them the x-intercepts if I cared about graphing the thing. But these are also called roots of the equation. So roots of equation. And that's kind of the term that we're going to use. And you might look at that and be like, okay, well, there's certain things I can do with the roots. So in year 11, at the start of extension 1, you would have seen polynomials. And there's certain things that you can do with the roots of a polynomial. So you might want to find the sum. Okay, and I know what the sum is. Like I've got both of the roots here, right? So, but I know that the sum is alpha plus beta, and we gave them Greek letters for pretty much no reason. And then we said that was the same as minus b on a. And according to just this here, minus b on a is just going to be 9 on 2. And I can verify this literally just by adding these two. So that's like 2 on 2. So if I add those, I've got 9 on 2 as well. So I can verify this. And I can also find my product. And that was alpha times beta. And that was, is it c on a? Yeah, c on a. Okay, and my c value is 7, my a value is 2. So that's 7 on 2. Or I could just times them. That times 1, I'm pretty sure, is just 7 on 2. So these are the sort of things we can find. And that's kind of as far as we've gone with polynomials. But there's an extra thing, I guess, or sorry, a different case of this expression. And it'd be one where we can't actually find any roots. So if I considered something like, let's go consider. If I were to consider something like x squared plus 2x plus 2, and I would set that equal to 0. If I tried to investigate this, and I might want to do that using GeoGebra, I'd probably find that here's my axes. The parabola looks like this, so it doesn't actually cut the x-axis, and so therefore it wouldn't have any roots. So I guess a different way would be I'd look at this and I'd say, well, can I factorize it? I can't think of two numbers that add n times to 2. So then I would probably resort to the quadratic formula. So x is equal to minus b plus or minus the square root of b squared minus 4 times a times c. So 4 times 1 times 2 all over 2a, which is just 2. So that's going to be minus 2 plus or minus, and now I've got the square root of minus 4 all on 2. And so this was a problem because we found that the discriminant is less than 0. And then what we would say is therefore no, and then we'd say the word real roots. So no real roots, you might have heard that before. Or you might say no solutions, no x-intercepts. And then if we kind of looked at a little bit of an extra step, which is what we did previously, why don't we try and consider what the roots of this thing might look like if we actually had roots. So let's just look at the sum and the product. Keep in mind that these are equal to minus b on a and c on a. So minus b on a would be minus 2 on 1, so minus 2. And the product would be c on a, so c on a, so 2. And so now I actually have values for my sum and my product, but I'm saying here that there's no roots. That's kind of weird. In other words, we're kind of looking for something that doesn't exist. It's not really real, but I guess if you think of the opposite of the word real, we might be looking at things that are imaginary. And to be able to comprehend something like that, we kind of need an expansion of what we consider to be a number. And so then I guess we can kind of start looking at the certain subsets of numbers themselves. So we kind of start with the natural numbers. So draw it like that, the natural numbers being 1, 2, 3, like your counting numbers. And then that's my natural numbers. And an expansion of that, if I can't count anymore, what I can do is start going backwards, and that's called an integer. That's not thick enough. So my integers like -2, -1, 0, 1, 2. So it's the natural numbers plus the negative numbers. And so then that kind of encompasses that. One extra step is the real numbers. So all the real numbers, signified by that R there, all the real numbers are just any genuine number that is in between any of the integers. So like fractions, decimals, pi, e, square root of 2, stuff like that. And inside here you've got so inside your real numbers you've got like the irrationals and the rationals. So rationals being things I can write as a fraction, irrationals things I can't write as a fraction. And encompassing all of this, and we'll look at it in a sec, encompassing all of this are our complex numbers. And our complex numbers are made up of imaginary numbers. And so we'll see what all that means in a second. But that's kind of how our number system works. So we just require, in order to consider why there's a sum and a product of these two unreal roots, we need to expand our current number system. And so now if we continue with our problem, so I'm going to just start off with this expression I've got here. So I've got x is equal to minus 2 plus the square root of -4 on 2. And I've also got -2 minus square root of -4 on 2. So they're my current roots. Obviously they're not real, but there's something we can kind of do to simplify these. And it's if we investigate this root 4 here, this root -4, sorry. So since minus root 4, we can kind of simplify this because like we've got 4s and 2s and stuff. So let's make this as easy as possible on ourselves. I can rewrite that as the square root of 4 times -1. And then I can write it as root 4 root -1. I can write that as 2 root -1. And so then I've got here -2 plus 2 root -1 on 2. And I've got oops, that looks terrible, -2 minus 2 root -1. Okay, and then all these things are going to cancel, right? So that can go, 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 that can go. So what I've left with is -1 plus root minus 1 and -1 minus root minus 1. And it's like, why have I even done this? But now I have two nicer looking roots. Let's investigate why the sum and the product actually make any sense. So I know that the sum up here was equal to -2, so -2. Now, let's think about that. So if I were to add these two, so I'm going to add those two in these brackets, -1 plus root minus 1 plus -1 minus root minus 1. Okay, and that's equal to, so -2, and then plus that and minus that, they're going to cancel, and what I'm left with is -2. -2 equals -2. That's interesting. So what I'm actually left with makes sense. Now if I consider the product, if I just times these two, I was told before that the product is 2. So if I multiply these two, so I want it to equal to -1 plus root minus 1, -1 minus root minus 1. There's a lot of minuses and stuff. Okay, so FOIL, that times that is going to be 1. That times that is going to be plus root minus 1. That times that is going to be minus root minus 1. And then that times that is going to be -1. No. Is that right? -1? Yeah, no. +1. That times that. That times that. I feel like I've stuffed that up. Anyway. Okay. And then they're going to cancel, and I'm left with a 2. So I found that the product is also consistent. So what we can kind of say about this is this weird expression, the root minus 1. I'm not convinced about this. Why did that not work properly? Am I losing my mind? -1 times. Oh, okay. Yeah, right. That's going to be minus -1 plus 1. Yeah, so I was confusing myself. Anyway, so what we found is this expression root minus 1, which we considered to be kind of like illegal, like a thing that we're not allowed to do. It's still consistent in our number system. So we're still able to find the sum of the products given that I'm able to perform arithmetic with my root minus 1. So that leads us to believe, well, does that mean this root minus 1, I can actually use that to, I guess, further our investigation? And we can. So this is where we start looking at imaginary numbers. So an imaginary number, okay, like things like root minus 1, root minus 4, which we saw before, root minus 100. So anything of the form root minus n, that's an imaginary number. And so minus n squared, which I'll show you why, I can write as root n squared times root minus 1, which is n root minus 1. So anything of this form, I can rewrite as this, a multiple of root minus 1, and anything I can write like that is considered to be an imaginary number. And so here, n is just like a normal number, whereas this is imaginary. Okay, and so then now I have anything that's of the form root minus 1 times by something, we consider that to be imaginary, and we're going to make a replacement for this thing, and we're going to say that root minus 1, we're going to call that I for imaginary. And so then that leads us to the expression I squared, I just square both sides, equals -1. And you'll notice that now we're talking about things that when I square them, I end up with a negative, whereas before we were saying, okay, if I were to square something, it has to be greater than 0, and we called that real. So when I square something and I end up with a negative, we call that imaginary. I've written imaginary 3 times on the same page. I don't know why I did that. Anyway, so this is kind of our definition, or these two are our definitions of imaginary numbers. So maybe I'll give that a box because that's just a little bit important. Okay, so now that we know that these things are consistent, we're able to find sums and products that behave well with our normal numbers, we can start performing things with performing operations on our imaginary numbers. So things like 5i plus 7i Okay, that's oh my god, I can't add two numbers. That's 12i. So things like that I can do. So if I'm just adding two imaginary numbers, I'm considering it to be something like this. I'm considering this I to kind of be like a pronumeral. So things like x and x and x, because they are essentially. It's just instead of x, I've got root minus one or I. So these behave exactly as like terms and variables and stuff like that behave. So I can add them, I can subtract them. 3i minus 4i is going to be negative I. And things like multiplication we already know works. So if I found the product, like 3i times 4i is going to be 12i squared. Okay, and then when I think about things like I squared, I actually already know what that is. I squared is minus 1, so I'll go a little bit of a step further and say that this is minus 12, or maybe I'll illustrate it a little bit better. So that's minus 1, which is minus 12. So there's so many things we can do with these things now that we know that they exist, and we can start simplifying things in different ways. And so now that I've got this weird I squared that I was able to simplify, why don't I go a little bit of a step further and go, okay, well, what's I cubed? Well, that's I squared times I. I squared was minus 1, so that's just minus I. Okay, what about I to the power of 4? Well, that's I squared squared, right? So I squared is minus 1, so minus 1 squared is 1. So see how we can start looking at this? I to the power of 5. Well, that's I to the power of 4 times I. I to the power of 4 we just saw was 1 times I, so that's I. If I just went to I to the power of 6, that's I to the power of 5 times I, which is I times I, which is I squared, which is minus 1. And so we actually ended up going in this loop. So you can see that I cubed was minus 1, I to the power of 4 was 1, I to the power of 5, so that's minus I, 1, I, minus 1. And you'll notice that this actually starts alternating. So you go from minus I, 1, I, minus 1, and then I7 will start the loop again. So I7 will actually equal minus I. But you can keep doing that and can convince yourself that that's a thing. We haven't actually looked at division yet. So if I were to divide something, so something like 6i divided by 3i, it works exactly the same way as any variable would. So I guess I can rewrite this as 6i over 3i, and then these things cancel and make 2 on 1, and these i's actually also cancel, so I'm actually just left with 2 on 1, which is 2. So all these things abide by our normal number system. Now, if we return to our original problem, so the original problem, which is kind of our theme of investigation, we had our roots, x, our unreal roots, or our imaginary roots, were, now what were they? They were minus 1 plus root, so minus 1 plus root minus 1, minus 1 minus root minus 1. So these are our original roots. Now I can rewrite them because I know that root minus 1 is just I. So I can rewrite these as minus 1 plus I and minus 1 minus I, and where I is equal to square root of minus 1, so just in brackets. So now I have these two roots that are written in terms of imaginary numbers. And so this value here is real, and this value here is imaginary. And two things, so the sum of a real and imaginary number, so a real and an imaginary number, that is called a complex number. So the whole thing here, that is a complex number. Okay, so complex numbers. They are of the form. Now, we tend to move away from x. So see how I've called this x equals a complex number. We move towards z instead. So whenever you see a z, it's kind of like, okay, here's a root or a number or something, but I'm telling you pretty much that it's complex. So if you're ever solving something like, if you're ever asked to solve something like, what was our original problem? Something like this, okay, if you were looking at it in terms of complex numbers, or if this was in the complex numbers topic, or if this was in an exam and that it told you there was complex roots, or you were expecting there to be complex roots, instead of an x, they'd use a z. So there's no difference. It's just kind of warning you that you're going to have to deal with complex numbers here. So I call it Z is equal to, and then there's a real and imaginary part. So the real part is just a number. So the number, let's just call it A, and then it's added to an imaginary part. So generally some multiple of I. In this case, it's just 1, but you can see here that there's always multiples of I. So I just say B times I. Okay, and it's important to note that the A and the B here, they are just normal numbers. They're not like this B couldn't just be like 3i. There's already an I here. So the components here, they're just normal numbers, and one of them has an I attached to it. And so what we say is, oh, and also this I is root minus 1. So this is just our definition of complex numbers here. Okay, oh no, make a proper box, please. Cool. Okay, so in saying that, these two are our numbers. This here is our imaginary number, and we say that A is our real part of the complex number. So what we actually say is it's the real part of Z. So Z is our complex number. Z's this whole thing. The real part of it is this, okay? And B is our imaginary component. So it's the imaginary part, it's this, it's the number that's attached to the I. So we call that the imaginary number or imaginary component of Z. And so you'll see these quite often and kind of be asked about that. So Z, a complex number, I, our imaginary number, B is the imaginary part of the complex number, A is the real part of the complex number. And so the very last thing we're going to do is sometimes instead of, I guess, writing it like this or writing it like in terms of our real and imaginary part, sometimes it's written as an ordered pair. So ordered pair being like A, B. So sometimes you might see it like that. You're not going to see it very often because that kind of implies that you're looking at a coordinate. And if I was looking at a coordinate, this would be something I could graph. So if I drew up a quick graph, why did that not go straight? That's because I don't have that selected. So if I looked at my ordinary graph here, so obviously, obviously these go up by ones. Okay, I should have drawn this on the line. Oh well. Now we kind of need different names for our axes because in our ordered pair here, so this A and a B, we're not looking at an X and a Y value, are we? We're looking at a real and imaginary part. So you can kind of think about this as real and imaginary. Don't think of it like that, but that's just... Anyway, so the real part is like our old X value. So this would be the real axis. So generally you'll see an R there to signify that that's the real axis. And then the imaginary axis. So sometimes you see like I am, or just like an I to signify the imaginary part. And so these just go up by real numbers, whereas these go up by I, 2I, 3I, 4I. Same thing here, minus I, minus 2I, minus 3I, minus 4I, minus 1, minus 2, minus 3, minus 4. And this whole diagram has a couple of names. It's called the complex plane. Like the normal plane is called the Cartesian plane. So a Cartesian number is just a number. A complex number is this. So the complex plane. Or it might be called the Argon diagram. It's exactly the same thing. Argon's just the bloke that I guess was the first person to draw complex numbers on a plane. And so then this ordered pair here, if I looked at our original problem, so our original problem being these two, I can graph them. So minus 1 plus I. Minus 1, so minus 1 plus I. So that's going to be here. So let's do that in red. It's going to be here. So that is the point minus 1 plus I. Okay, and then the other one, minus 1 minus I. So minus 1 minus I is here. Minus 1 minus I. Okay, and because these are complex numbers, we call them Z equals, and there's two of them, so let's call this Z1, let's call that Z2. Okay, and we can actually, with complex numbers, draw them as vectors. So being, I don't know if you've started vectors, Quang, or you might, yeah. I don't know if you would have drawn one yet, but essentially it's just a point from the origin. So just draw out complex numbers like that, like little lines, rather than a coordinate. Yeah. And so that's kind of it. So I understand that I've thrown a lot at you there. That's quite literally a lot of the complex numbers topic, but it's just kind of like an introduction, just to play around with complex numbers a little bit. Just note that you can add them, subtract them, times, divide them, just like anything else. You can draw them. You can talk about their real and imaginary parts. You can write their real and imaginary parts in this notation. You can consider them an ordered pair. That ordered pair allows you to draw them. Just think about also, see how I've got -1 plus I and -1 minus I, and their relationship on this graph seems to be symmetric over the real axis, not the, I was about to say the x-axis, over the real axis. That's no coincidence. If I had -1 plus 2i and -1 minus 2i, that would also be, so that would be here and here, that would also be symmetric. So that is a relationship. Also keep note of these properties here, the I cubed, I4, I5, I6. If you keep going, there is a pattern. And if you were to write it in general, it's something like 4k plus 1 or something. I think you're able to write it as, I can't remember, but just every 4 iterations, it'll restart this little cycle. So that's no coincidence. So there's just a lot to unpack here. I'll obviously upload this, but we are going to go through this stuff much slower. It's just, this is kind of just like an introduction as to how things kind of came about. And yeah, I guess that's our introduction to complex numbers in a nutshell. And that's a long video. I don't really know. Yes, it is 26 minutes. Holy moly. All right. Anyway, goodbye.